Good morning, class. Today we're starting with section 2.4. And if you've been asking yourselves, when are we going to use these derivatives? Well, here we go. Section 2.4 and 2.5 will be going over applications. In this section, we're going to be talking about uninhibited and limited growth models. We're going to be given a derivative and finding the function that ended in that derivative, and then we're going to be solving application problems using exponential growth and limited growth models. Let's get started. Let's look at this theorem. It says a function y is equal to f of x satisfies the equation where the derivative of y with respect to x is k times y. In other words, it's a constant times the original function. Or f prime is equal to a constant times the original function. Let's think about that. When is the derivative equal to the original function with exception of a constant multiplier? Well, it's when the original function is e to the x. And so we know that this is true when we have e to the x with maybe a constant in front of it and maybe a constant multiplying by the x. And so we know that if that's the case, the derivative will have that original function in it. Let's see what that looks like when we apply this theorem. Find the general form of the function that satisfies the equation. dA dt is equal to 0.03a. And so notice that we have this multiplier in front of our function. That's the part of this multiplier, k. And so we know what the k value is. That's going to become this value here. And the rest of it is set for us. So we know that k is equal to 0.03. And when I write my function, I'm going to call it a of t. I know that because its name is a, and then the variable in it is t. My function is c e to the k, and then instead of x, I'm going to use t as my variable, since that's what's told to me. This is the answer right here. A of t is equal to c e to the power of 0.03t. But let's just check our work. What happens when I find the derivative of this function? When I find the derivative of a of t, I'm going to have the constant multiplier. I'm going to have e to the 0.03t, and then I'm going to chain rule it, and I'm going to multiply it by the derivative of that power. And so you end up with 0.03 ce to the 0.03t, which is the same thing as 0.03 times a, since this whole thing here is equal to my a function. And so you can see that the derivative is exactly what we thought it would be if this is the function that we were looking for. I know you're probably asking yourselves, what is that c hanging out in that function? It's not a variable, it's a constant. And so it could be any constant. That is, if you had the function a of t is equal to 2 e to the 0.03t, and you took the derivative, it would still work out like this. Or instead of 2, you could use 5. Or instead of 5, you could use 14. It doesn't matter what number you put here, the derivative would work out like this. And so that c stands for any constant that you can think of that you want to put there. Notice that video example 2 says to solve the differential equation. What this means is the same instructions as our last example. It means that they're giving us a derivative and that we want to find the original function that generates this derivative. And so in order to do that, we're going to use the theorem again. I'm just writing the general form of the equation. We do know that the k value will be 0.25. And so to find our original function is equal to c e to the 0.25t. And therefore we've solved the differential equation by finding the function that gives us this as our derivative. When you read uninhibited population growth, that's usually modeled by an exponential equation. It starts off with the c or a p naught, which is the initial population, and then it grows exponentially. It's uninhibited because as you grow exponentially, it goes up, and there's no ceiling to how far it can grow. This can describe population of humans, bacteria in a culture, dollars invested in continuously compounded interest. All of these different scenarios can be described with uninhibited population growth. Suppose that an amount P0 in dollars is invested in a savings account where the interest is compounded continuously at 4% per year. That is, the balance P grows at the rate given by dP dt is equal to 0.04p. We can make this equation because we know it's compounded continuously at 4% per year, and then we know that that's the rate of change of this function. And so we identify that the rate is 0.04. Find the function that satisfies the equation. Okay, we're going to write that. That's going to be P of t. Once again, getting that from dP dt. We know that we have c e to the kt. Instead of c, we're going to use P0 e to the 0.04 times t. There's our equation. Part B asks us, suppose that $10,000 is invested. If we invest $10,000, then that's our P0. So let's rewrite our equation. That would make us have P of t is equal to 10,000 e to the 0.04 t. What's the balance after 1 year? That's plugging that into the calculator. You want to put P of 1, and that would just be 0.04 as our exponent times 1. The calculator tells me that's $10,408 and 1077 cents. So let's write that in the better way with our dollar sign. And then rounding to the nearest cent, we'd have 11 cents. If $10,000 is invested, how fast is the balance growing at 1 year? Well, before we can find that out, we have to take the derivative. And that would be 10,000 e to the 0.04t times 0.04. And that's doing the chain rule, doing the derivative of the inside. But notice that that's also what we started off with. The derivative is 0.04 times our original function. This is the original function times 0.04. If we multiply it out, 10,000 times 0.04 is 400 e to the 0.04t. So asking ourselves what's the rate of change at 1 year would be plugging 1 into this function. The calculator gives me approximately $416.32. And then we know that it's dP over dt, so that's over a change in time per year. So it's changing at a rate of $416.32 per year. The world population was approximately 6.0400 billion at the beginning of 2000. It has been estimated that the population is growing exponentially at the rate of 0.016 or 1.6% per year. Thus, we have the equation dP dt is equal to 0.016p, where t is the time in years after 2000. Find the function that satisfies the equation. Assume that the initial population is 6.0400 and our rate of change is 0.016. Pulling on our previous theorem, we know that P of t will be 6.0400 e to the k t. Now that we have our population function, we can now estimate the world population at the beginning of 2020. Notice that 2020 would be 20 years after 2000, and so my t value will be equal to 20 at the year 2020. So P of 20 is 6.0400 e to the 0.016 times 20. And then you can use your calculators to approximate this. Using the calculator, I got 8.317851,697. Now that's too many digits. Let's count how many there were here. If we have 4 digits after the decimal point, that's what we want to replicate when we're doing this. So we're going to say 8.3179 billion people. You always want your answers to be in the same format that your question was, which is why they included 4 decimal places, even though some of those were zeros and weren't technically necessary. They included that many spaces to tell you as a clue how many spaces you need in your answer. Part C asks us to find the rate of change of the population at the beginning of 2020. And so before we can find the rate of change, we have to find the derivative. And that would be the original function, including all of this part, times the derivative of the exponent, which gives us 0.016. And then let's use our calculators to simplify that. Using our calculators to multiply the 6.0400 times the 0.016 gives me 0.09664. And then we're going to write e to the 0.016t. Let's plug in 20 into p prime. And then let's use our calculators to find this answer. My calculator says that's 0.1330856. Once again, let's write that with the correct number of digits, just 4 decimal places after the decimal point. So that'd be 0.1331 billion people. That would be per year. As always, it's going to be dp dt, so that's going to be the change in population over the change in time. So that's going to be an increase in 0.1331 billion people per year. The previous models of uninhibited growth was the exponential function, where you could just see the graph go up exponentially, and there was no ceiling to how much it could grow. But now we have models of limited growth. That is, they have a fraction where the top is L. L is the limit to how high something can grow. And then the bottom is 1 plus this value. Notice it has a negative coefficient on that exponent. And so that's going to, as my values increase, this number gets smaller and smaller and smaller. And so then ends up becoming just a 1. And so L divided by 1 is L. And so you have a population that starts off small, and as it grows, it starts growing exponentially. Then as it starts reaching the ceiling of the limit of how much it can grow, then it starts tapering off and stops growing as fast, because there's maybe something inhibiting the growth, maybe a limitation on food, living space, or other natural resources. So they're going to be limited in how far they can grow. Spread by skin-to-skin contact or via shared towels or clothing, methicillin-resistant Staphylococcus aureus, or MRSA, can easily spread a staph infection throughout a university. Left unchecked, the number of cases of MRSA on a university campus T weeks after the first cases occur can be modeled by N of T is equal to 568.803 divided by 1 plus 62.200 e to the negative 0.092t. Find the number of infected students after 3 weeks, after 40 weeks, and after 80 weeks. So in order to do that, we just need to find N of 3, N of 40, and N of 80. I'm going to use my table function on my calculator. In order to use the table function, I'm going to press the y equals on my calculator. I'm going to put this as my y equals, and don't forget to put parentheses around your entire denominator to make sure that it does the correct work. Using my calculator, I then went to the table and I plugged in the values of 3, 40, and 80. I also plugged in a few other numbers just to make sure that this was the correct value and that I was plugging in correctly. And so I know that there's a limit. We saw that graph before. We know that the limit's going to go up to here, and that the limit would be this numerator. So that would be 568. And so I started plugging in large numbers like what happens if I go to 1,000 or maybe 10,000 or something else. And as my n got increasingly large, my answers were close to what the limit should be. And so I feel like I correctly inputted it. And then when I put these values in the table, n of 3 gave me 11.801. N of 40 gave me 221.42. And n of 80 gave me 547.15. Let's look back at the question. It says, find the number of infected students after 3 weeks. We would want to round this to 12 students, 221 students, and 547 students. Because you can't have half a student or 0.8 students. So we would want to give those answers in integers. Okay, moving on to part B. It asks us to find the rate at which the disease is spreading after 20 weeks. So we need to find n prime of t, and then when we're done finding that, we need to get n prime of 20. It is a quotient, so you do want to do the quotient rule. So I put the quotient rule right here for us to refer to. Remember that the derivative is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. So I wrote all of it out, but we have the denominator times the numerator's derivative, and the numerator was just a constant, so this whole thing goes away to 0. And then we had another 0 here, so we just need to multiply the 568.803 times the 62.200 times the negative 0.092 to simplify that numerator. So this is what I get when I simplify the negative 568 times the 62.2 times the 0.092. I get this value here. I put this into my y equals on my calculator, and then I use the table function to find n prime of 20. It gave me approximately 4.368. What does this number represent? Remember that it represents how many number of cases per week. And so that's going to be 4.368 new cases per week. That's the rate of change around 20 weeks. Part C asks us to explain why an uninhibited growth model is inappropriate, but a logistic equation is appropriate for this situation. And then it asks us to use a calculator to graph the equation. The reason why we can't use an uninhibited growth model is because we have a limited population of students. So as students become infected, there's less students who are uninfected. There's a limited number of cases that can actually happen. The logistic equation is more appropriate for the situation because there will be a sharp rise in how many students get it in the beginning, and then it'll taper off as more students are infected. And so you have that limited growth. Let's actually graph it using a graphing calculator. As we look at the graphing calculator model of our equation, we can see that there's an initial rise in diseased students, and then it tapers off as they get closer to 568 students, and that's the limit. This number up here is our limit, is the numerator of our function, and then you see that the graph, it goes up and then it tapers off as we reach that limit.